Good day, folks. This is tutorial number 16 on December 31st, 2025. It will be the last video that I'm going to be doing for this year, and it deals with the force vibration of a disc, which is modeled as a bushing, with a bushing functionality. It is closely related to tutorial 15 because there I did a free vibration of the same problem and I used bushing in order to model the torsional stiffnesses. But here we are applying torque, okay? The basic few slides is pretty much the same as 2015, except that the equation of motion becomes J theta double dot. That's uh, mass moment of inertia times angular acceleration equal to all the forces, and there is a resistive force because of the spring, and then there is a load theta, a torque T that's applied there. There's a mistake here. That should be plus T, not minus T. Okay, now what we do is we're going to model this shaft. This shaft, we're going to model it as a torsional spring, and the stiffness of that spring based on the material property and the dimension of it is given in most strength of material books, and it's given here. Okay. Now, if you're interested in free vibration, then the natural frequency is going to be the ratio of k over j taken square root of it. It's right there, and that's what we did in 15. What I'm going to do is that shaft, because we already calculate using hand calculation the stiffness, torsional stiffness of it. We're not going to model that shaft in its exact dimensions. However, I will draw something which will play the role of that shaft. I need that, and I later on specify the correct properties, stiffness property based on how hand calculation that we're doing it. So these are the dimensions. So that based on that, K is going to be 176, roughly 176 appropriate unit. And the disk is modeled like that. And based on these dimensions and the fact that the steel is made out of steel, the mass of it will come out to be 100 kilogram. Okay. Now, I made a mistake. If you in tutorial 15, I had a mistake here. It was T equal to 10.8, although the calculations and everything was correct, except that in the slide, I had 10.8 instead of 108. That's why keep that in mind. Okay. Now, we're going to do two problems. First is the constant load. Apply a constant load of T1, no damping involved in this tutorial. So, very based on zero initial condition, one can actually solve this problem analytically, and you're going to get what you see up here. So, if you use T of 10 and K, we just calculated, this is what we're going to be comparing with the 3D Experiences platform. Now, then after I do this problem, I go and apply a sinusoidal harmonic torque, and this omega is big omega is the driving frequency. Some textbook write this thing as little omega sub d, means driving frequency, to distinguish it from little omega sub n. But here we use big omega. Now, if you look at the strength of material book or vibration book, introductory vibration book, you see that this angular position is going to be proportional. Now, it's not only T naught, there's some other stuff here. There is a square root of dot, 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 but we are not interested in that. So it's going to be proportional to T naught, and the frequency of oscillation is going to be same as the driving frequency. So if I put T naught here as 10 and omega as 5, let me assume that omega is 5, big omega is 5, then you work it out. We're going to compare our result with something that looks like that. A couple of comments. In tutorial 15, I was doing free vibration. That's why when I created my bushing is an axis-based element, basically. So you need to assign axis associated with this bushing. I had to, one of them is the axis associated with the shaft, which we're modeling it like that as far as the size goes. This is a lot taller and a lot skinnier, but remember, we're going to use the proper K in it instead. And this is the axis system for the disk. And notice that they are actually aligned. I don't have to rotate this thing. In the tutorial 15, I took this thing and rotated it by 20 degrees so that there is an offset between these two, so that there is a restoring force once you let the disc go. But I don't have to do that here because we are applying a torque action. Okay, so we're gonna need a revolute between this dummy, call it wall or dummy shaft, and then the disc, rotating disc, and then we need a bushing element too. So here is a revolute and spring element, which actually is a bushing. And this is the property of the stiffness of the torsional spring based on hand calculation. If you want damping, you click on that tab and you put the appropriate damping value. Make sure that both revolute and spring are included. Excuse me. And notice that when we apply material properties, the wall doesn't matter. It can be any dummy thing, but then you do need initial properties for it. But the rotating disc, based on the dimensions that I have, and clicking this checkbox so that it uses density of the steel, is going to come out to be 100 kilogram. And notice that your moment of inertia about Z is also 1.9, as it's supposed to be. Okay. Now, because it's a dynamic problem, we're going to dynamic scenario. We're going to be applying a torque excitation, and the two integrator, as you know, one of them is DASSL, and the other one is symplectic Euler. I use this default DASSL, and I do it over 4-second interval. Now, if you want to know more about bushing, you have to go to the online documentation, which is not very clear. Okay, let's go ahead and make it. So I'm going to start with an assembly. And I first of all include the shaft in it, the dummy shaft actually. Insert, right click properties, dummy shaft. Okay, let me copy this and paste it there. Okay, let's go make it. So double click on that. On a convenient plane, on that horizontal plane, I will sketch a circle. That circle is going to represent our basically shaft. So something like that. Let me give some dimension here. I'll make it maybe 10 millimeters. This is totally irrelevant, but we're going to make it. Exit, and then pad it in the opposite direction. Again, the length of it doesn't matter. Okay, so what you see here is actually, what is this? Is actually this in the middle. Okay, now, excuse me, I mean, I have a cold before you go away. So click on the axis system here. It creates the axis system associated with the dummy shaft. Now go all the way to the top, insert the rotating disc, insert the 3D part, right click properties, rotating mass, how about rotating disc? Okay, copy that. Say okay. Now we're going to make it. Double click on a convenient plane, on that bottom plane. I will sketch a circle. That's going to be my disc. Okay. Let me give the correct radius, which was 108 millimeter. Remember I said I made a mistake in the slides for free vibration. Exit. I'm sorry. That radius, that's a mistake. That radius was 195, not 108. This was 195 millimeter. Sorry. Exit. And then pad it by 108. In the other direction, 108 millimeter. Oops. 108 millimeter. So this is going to be my disc. So what you see here is there is that dummy shaft and there is the disc. Let me create a coordinate system down here. So there are different ways of doing it. So let me create a point down there. I create a point down here, and then I create my axis system while I'm in rotating this. And for the origin of it, I take that point down there, and notice that they are lined up in the vibration. Free vibration, I have to go and rotate this thing by 20 degrees or so. Okay, that's fine. Now, let me also create a point on the periphery here, because later on I will, let's see now on a curve, because later on I want to put a sensor somewhere. Okay, that's good. Good. Now we're going to apply the properties of these things. So let me collapse these things. We go to the mechanical systems design. This is where we apply our material properties. Make sure that to go there, first you are at the top level, not at the part design. That's why it didn't take me to the right spot. I'm part design. Then you go to mechanical systems. Okay. All right. So we are in mechanical systems, and if you all the way to the right, you see the weight here, weight definition. You click on it. Everything is unknown here. Select the dummy shaft, and move this thing out of the way. Click on this to put the steel properties on it. That's totally irrelevant because we're not using this. It's just, oh, I'm sorry. Which one is this? Yeah, that's the dummy shaft because it's going to be stationary anyways. You close that and then click on the rotating disc, click on the hyperlink, properties of steel, almost 100 kilogram. Okay, almost 100 kilogram. And there is your 1.9 that you had it in this slide. Okay, that's good. All right, so let's get rid of this. All right, so let's go ahead and create our stuff. Should we do the revolute joint? So, well, first of all, let's fix something. Where is that? Uh, these are the engineering connection. Fix the dummy shaft. Okay, we fixed it. You can see that. Then let's do the revolute. So the revolute between the dummy shaft and the disc. So revolute. And the template that I'm going to be using is this fourth one. Doesn't matter. This axis and the axis of this dummy shaft, and this plane and the plane of the dummy shaft, right there. And I don't really need to control this thing. I can just either delete it or leave it the way it is, not used. That's all. And say no. So I created my revolute, and then you're going to do the bushing right there. Bushing. Okay, so well, for the support, you need the two axis system. One of them is for example, the one for the shaft. Excuse me. The second one is the one for the disc, and you click on the elasticity, click on the f of x, and there's the stiffness, 176 point. I put down 7, but I think it should be 175. But I'll use okay. I'll use 7, whatever I told you. That's fine. If there is the damping, then you go and get the tab and put the damping in it. Well, I'm not going to do that right now. Okay, so that's pretty much it. There's nothing else to do. So let's go ahead and create our mechanism. And let's check it out. Mechanical Design Manager, make sure that these are all included because sometimes when you add joints later on, these are not included. You have to make sure they are included. That takes care of this. Let's go and change uh, applications. We're going to go to Mechanical Systems Experience. Okay, let's create that. First thing we're going to do is we apply torque. Here's the torque excitation. Okay. And it says, what is the support? The support is this rotating body right there. The point of application, we can select that point that I remember I created a point at that bottom of this disk. So let me go ahead and select that because it wants you to pick a point. Okay, so I'll select the first point. Second one was for the probe. For the axis, I can select, for example, this Z axis or this axis. It doesn't really matter. And you put down here is, I think I put down 10, right? 10. Good. So the probe, and there's a probe here we're going to create at that location. If you want to monitor things at that location. And now dynamic scenario, we created a torque, we created a probe, we send it to the right hand side. We go to the parameter, DASSL, and over 4-second interval. It's a constant torque, and it's going to oscillate back and forth about a non-zero angle. Okay, so let's go ahead and run it. Okay, let's go check something. Plot this, deselect all. So let us plot the uh, angle. Vertex, well, let's check, for example, angular velocity. How about that? Angular velocity. Remember, this thing oscillates and then it stops, right? So then it's oscillate, then it stops. So let's look at angular velocity magnitude. Angular velocity, hang in there. Magnitude. uh, let me check something else because I didn't like what I saw. Let's go ahead and check out bushing. Here's the bushing. Click on the bushing and see oh, it says FX. That should be MZ 176.7. I put it at the wrong spot. That's why there was no stiffness. That kept going on and on and on. Angular velocity kept increasing. Okay, we're in business. Right click, run it. You see that? Now it's oscillating because there's a spring that uh, takes care of the motion, restoring force. And go there. Let's go ahead and check deselect everything, angular velocity. Let's see, where's angular linear velocity, the magnitude, that should be periodic, right? With a period, that is actually double of this period. Actually, let me see for a second. Let me see here. Let's go back here. Right there. No, sorry, the period which is equal to this, not double of it. 0.652, and that you can see it's 0.652. In fact, if your numbers, you can go and check it, but it is correct. This distance is almost 0.6. Okay, now, so what we want to do is repeat the same problem, except that the load is not constant anymore. So let me go ahead and double click on the torque excitation and put the cursor here. Let's say right click, edit formula. And this is where you can start writing formulas. So, for example, n n x m times sine of parentheses. What was that? 5 rad underscore s. 5 rad underscore s times time. Hopefully, there's no syntax error here. Good. See that? Okay, so let's go ahead and run it. This is on the high sinusoidal loading. So let's go ahead and plot. Again, different things. For example, let's go ahead and look at the angular velocity magnitude. Okay. This is under harmonic loading. It's not a simple situation as what I have written here. Okay. Now, in the event that you want to include damping, let me close that. In the event that you want to include damping, as a matter of fact, let me go ahead. Let me go back there. Let me go back there. Change this thing back to Uh, you can change it back to 10 point Newton times meter. Okay, constant. And you can go to, for example, the bushing. Click on the damping, MZ, put a 5. If we want to use the same damping that I had uh, written down in tutorial 15, and let's run it, and you'll see that what's going to happen, these amplitudes, the amplitude of angular velocity is going to gradually die down as time goes on. I did it over a 4-second interval, but where's that? Angular velocity, magnitude, you can see. All right. Good luck, folks. Before I stop this thing, one thing I should say, as of today, I have not been able to find any explanation of why is it that one cannot write a few lines of code for an arbitrary torque distribution. Okay, it won't take it, or at least I don't know how to do it.